Very good afternoon and warm welcome to Parallel Technical Session 13. Welcome to the chairman of the session, Professor D.K. Vaidya, and co-chair, Dr. Asha M. Nair. And welcome to the SOAP lecture speaker and to all the technical paper presenters. Before I hand over the session to the chairs, for the information of the delegates who are there in the 3D platform, let me share the platform and explain how you can post your questions. And also our guests can see the platform here. So I hope my screen is visible. So this is the platform that we have, the virtual platform where the delegates will be attending from there, where the speakers are actually in the Zoom platform. So our session is in Hall A, the current session. So once you play here, it is live actually. You can watch what is happening in the Hall A. So this is, there will be some 10 seconds lag is there. Anyway, I will close there, otherwise there will be echo. So to post any question, you can see a tab actually on top left, adjacent to the lobby. You can click Q&A and you can type your question there. So the delegates can type your question here in the Q&A, which is adjacent to the lobby on top left. So that the chairs will get it here and the speakers will be answering. So I just wanted to share this information so that delegates do not get confused where to ask question. Well, it is my pleasure to introduce the chair and co-chair of the session. The chairman, Professor D.K. Vaidya, is a professor at I.I.T. Kharagpur, and he obtained his PhD from Indian Institute of Science, Bengaluru. He has over 27 years of experience in teaching and research and published over 125 papers in several national and international journals, as well as in the conferences. He provided consultancy services to various industrial problems from National Highway Authority of India, Kolkata Port, Public Works Department, Tata Mines, Indian Railways, etc. Professor Vaidya also held several administrative positions at IIT Kharagpur, including chairman as well as vice chairman of the JE for IIT Kharagpur zone for 1 year each. And he has also visited several countries abroad for presenting papers and delivering invited talks. And also he served as a faculty member in the University of West Indies for 2 years.
Thank you.
Dr. Asha M. Nair, co-chair of the session, is a professor in civil engineering at Department of Civil Engineering in the CMR Institute of Technology, Bangalore. She obtained his PhD from I.I.Sc Bangalore in 2011. Her areas of research includes use of waste materials in construction, use of geosynthetics in low volume roads, and fatigue behavior of concrete and asphalt. She published more than 30 research papers in reputed international journals and conferences. Welcome, madam.
Thank you.
Thank you. Thank you.
Now I hand over the session to the chair and co-chair.
So I once again welcome you all this particular session. And it is my pleasure to introduce the speaker, the special lecture by Professor Gabriele. Is a senior lecturer in Geotechnical Engineering at the University of Canterbury. And his research focuses mainly in earthquake engineering and related problems. And he received his PhD degree in geotechnical engineering at University of Tokyo, Japan. And Dr. Gabriele has authored over 100 scientific publications, mostly in geotechnical earthquake engineering. And he has awarded the prestigious Japanese fellowship in 2014. Also, Gabriele was the team leader of the 2016 NJSEE Learning from Earthquake in Kumamoto, Japan, and team co-leader of the 2015 JGS and JSC in Earthquake Mission in Gorkha, Nepal. So with this brief introduction, I welcome Professor Gabriele for give his lecture. Thank you.
Thank you very much, Professor, for the kind introduction. I will share my screen, and I hope you can see. Can you see my screen?
Yeah, it's coming.
Okay, perfect. It is my great pleasure to deliver this State of the Art and Practice lectures, and I would like to thank you, the organizing committee, for giving me this great opportunity. I just realized my bio was a bit old since we have COVID. In the meantime, I was promoted associate professor at the University of Canterbury. The topic I'm going to cover today is the cyclic resistance and large deformation characteristic of sand under sloping ground conditions, and I will provide some insight using a state-of-the-art apparatus, which is the torsional shear apparatus, which is capable to achieve extremely large deformation. This is the outline of my presentation. I will start with provide some background information and then going through the key objective of the research that I'm going to summarize today. Is a research that started more or less 10 years ago and in collaboration with the University of Tokyo. Then I will talk in particular about the testing apparatus, and then I will show what is the testing material and briefly talk about the procedures. And then I will really focus on the test results, and I will talk about the failure modes that were observed in the laboratory. And then I will move on the cyclic resistance of sandy soils, looking from a small strains up to extremely large strains, and I will provide some new insight in that particular regard toward the large strains. Then I will talk about the strain equalizations that can be observed in the laboratory in liquefied soils, and I will show how the results that were obtained using this novel apparatus can be actually used to predict or to back calculate what is the failure of slopes that was observed during past earthquake in the field. And then I will conclude my presentation with some very brief concluding remarks. So let's start with some background. So the photo shown here shows the failure of a slope occurred in 1964 in Japan following a Niigata earthquake. It was a really moderate slope, a gentle slope. The inclination is only 2% or even less. But as you can see from the photos, the damage to building infrastructures and roads and lifeline facilities was quite severe. So it's only 2% slope gradients, but it's a slope made of clean sand, dune sand, which was very close to the river. In fact, the slope to move toward the river for about 8 meters. And therefore, the photos and the damage associated with the liquefaction are shown in this historical photos. So the deformation at 8 meters, and if you consider the average thickness of the liquefied layer is 4 meters, means that basically the deformation on site were on the order of 200%, extremely large shear deformations. So this is an historical case, but also there are more recent cases. For example, in 2015, these two photos here, A1 and 2, shows the liquefaction of non-plastic silty soil, finds only more or less 90% of silt. But you can see the evidence of liquefaction here, the typical sand boils and some fissures in here. But the liquefaction occurred in a gentle slope. Was again, the inclination was 1 or 2% near the Trigely River, and as you can see here, there were large fissures and a lateral spreading for many, many meters, and also going backward from the river about 50 or 100 meters. The other case I'm showing here, it's the failure of a slope occurred in Japan due to the Kumamoto earthquake. In this particular case, is a volcanic soil, it's pumice soil, weather pumice soils, which was sandwiched between impermeable layers of clay. And I will come back to this particular slope later on with more information. But the peculiarity is that the slope again was only 6% in terms of inclination, but the soil cover a distance of 600 meters from the source to the deposition area, and on the way impacted against a new residential complex, destroying 7 houses and killing 5 people. So I show some historical cases, more recent cases, but the key issue is that when it comes to liquefaction of sands in slope grounds, still we have a lot of uncertainties, and we have the design or our capability to predict liquefaction is still largely unknown. And the reason is that the phenomenon is quite complex, and also the way or our capability to test this material in the laboratory is still challenging. So one of the key aspects is that if you look at the stress condition of slope ground before the earthquakes, we already have a component or initial static shear due to the gravitational effect, in addition, of course, to the vertical horizontal stresses. When it comes then an earthquake, we have an additional component, which is the cyclic stress ratio, cyclic stress, that is in addition to the initial static shear. And the sum of these two components, starting and cyclic stress ratio, give us two stresses. The one that I call maximum shear stresses, when the cyclic shear stress and the cyclic shear stress act downward in the same direction, and one is the minimum, when the static and the cyclic shear stress act in the opposite directions. Of course, the combination of the tau max and tau minimum provides us information how the soils really experience the cyclic loading. In some cases, the combination of these two loads give us the classic stress reversal, where the loads change from a positive value, a maximum positive value, to a minimum positive value. And I will show you that this is the key factor for liquefaction. But if the slope is quite, the inclination slope is quite more than 6 on 10%, and it means the static shear is quite high, very often we don't have the reversal stresses. And this will be another key factor I will show later, that might not trigger liquefaction, but still might be detrimental and might trigger the shear failure of soil. So the initial static shear has been recognized one of the key aspects in regards to the liquefaction in sloping ground, and to evaluate also the effect of liquefaction. Yet, if you look at some of the early studies, starting in 1967, just after the 1964 negative earthquakes, at the same time there was another earthquake in Alaska at the same time, many studies have been done using structural apparatus, but also try to mimic the simple shear conditions, which are more realistic of the stress condition in the field. But if you look at some of the results, the conclusion of some of the preliminary studies, we can see that the effect of static shear is not yet clear. Some tests shows the liquefaction resistance increases with initial static shear. Some other tests show that it decreases with initial static shear. It's not only when we have different testing devices, but even within using the same testing apparatus for some structural apparatus or simple shear conditions, still there is not it's not very clear what is the effect of initial static shear. If we have a very close look, then we realize that some of the inconsistency might be because maybe the relative density of the soils tested were different, or the criteria to define liquefaction was different, or the level of deformations that were used to define liquefaction, or the strength of the soil were different. So I will try to use some of these parameters to clarify what is really the effect of initial static shear. The other aspect is that if you look at the level of deformation we can achieve in the laboratory using conventional apparatus, we are on the order 20-25%. But as I showed before, in the field, we have more than 20-25%. So we need to really have something, new capabilities in laboratory that can help us to study the larger deformations and understand when liquefaction occurs in the post-liquefaction stage. Can we expect larger deformation, or can we predict based on laboratory tests and all the tools that we have? In these two pictures here, the figures in here, I should compare what is the strength of soil in sloping ground using simple shear conditions, so in this case, and triaxial apparatus. So we have two clean sands and tested with similar densities, and you can see that in the case of simple shear, it looks like the initial static shear has a detrimental effect for mostly from loose to medium dense sand, but doesn't have a major effect. Actually, it's beneficial in the case of dense soil. Now, if you look at the other case, the triaxial test apparatus, tests, we can see that in most of the case, it really doesn't matter which density range we look, might be from 10% to 50%, 70%. It looks like that initial static shear has always a beneficial effect. And the reason because the triaxial apparatus might introduce a certain anisotropy in terms of deformations. We know that in the triaxial apparatus, the deformation tends to accumulate in the extension side of the soil behavior. But the question is that is the triaxial apparatus the best apparatus to reproduce the stress condition in the field? So what we evaluate in the laboratory, yes, is the true behavior of the soils under triaxial conditions, but they are not really representative of the field conditions. On the other side, the simple shear apparatus help us or provide us an opportunity to really closely replicate the simple shear conditions. In order to clarify some of the aspects regards to the effect of static shear on the liquefaction behavior of soil and sloping ground, and also with the intention to be able to evaluate the large behavior of soils, we use a special apparatus. So we try to simulate the larger strain behavior of liquefiable sand sloping ground. That was the key objective, but also we try to identify what are the potential failure modes of the soils, depending on the combination of cycling and cycling, static and cyclic restorations. Then we define the liquefaction resistance from small to large strain levels. And also we assess what was the strain localization in liquefied sands. To do so, of course, we try to simulate as much as possible in a realistic way the behavior of soil. And in this particular study, we use a different combination of static shear stress, cyclic shear stress, and soil density. And because the tests I'm going to show are quite time consuming, each test takes at least 1 week, and on average, only one test every month is successful. There is a lot of things that can go wrong in these tests. In this particular presentation, I'm not going to touch the confining pressure effect. Okay, so I'll only focus on the first three key factors. Moving on the testing apparatus. So the apparatus we use in the study is a large strain torsion shear apparatus. So this is not a commercial apparatus, is a unique apparatus built at University of Tokyo, with very unique capabilities. We test a hollow cylinder apparatus. So in this particular case, we could control for a degree of freedom, so the vertical stress, the horizontal stress, but the torsion shear stress, but also in terms of vertical horizontal stress, you can control both the outer and inner pressure acting on the specimen. So this is a photo of how looks the apparatus. It's quite large apparatus, has a special loading systems with a gear that allows to apply strain control or strain rate control tests. So you can even evaluate the post-peak behavior in monotonic tests or even in cyclic tests. And also allows to achieve in terms of double amplitude, more than 100%. Okay, so really pushing the boundaries and exceeding large deformations. The other thing it's capable to do is apply the quasi-simple shear conditions by mechanically locking the height of the specimen. So the vertical deformation are 0, and you can apply directly the shear rotating top cap. And the only thing, the other things is to have the simple shear conditions. You have to assume that the radial and circumferential deformation might occur, but they will self-balance each other. So we call these quasi-simple shear conditions. This is a photo of typical specimen large deformations. The specimen we could test has an outer diameter 150 millimeters, the inner diameter 90 millimeters, and the height is 30 millimeters. So extremely large specimens. The material tested in this particular presentation is Toyota sand, which is a clean quartz-rich sand, heavily studied in Japan, so we know all the informations, and we can easily compare our results with past studies and also triaxial apparatus and all the sort of studies. So we have done a large number of tests. So the tests I summarize in the paper are only 26, but in the meantime, I had a PhD student finishing, and therefore we have more test results. And then the yellow table here, I will use some of the additional test results on relatively dense sand. So I will talk about the behavior of relatively loose sand, medium sand, around 40% relative density, but also I will use data for dense sand with relative density about 70–75%. So now moving on the test results. So before starting, I will use this table here. So the idea is that the initial static shears is a key component on the liquefaction behavior of sand and sloping ground. But also we know that the combination of the static shear and cyclic shear might have a key effect, because you might have if the cyclic stress ratio is greater than static shear, the soil will experience the so-called reversal stress conditions. But if the static shear is larger than cyclic shear, then we expect the stress will be always positive and the non-reversal stress condition will apply. On the other hand, also I mentioned that the maximum shear stress is an important parameter, so which is the combination, the sum of the static and cyclic stress ratios. But also, as I will show later on, the comparison of the maximum shear stress we apply during the tests compared with the strength of the soil, this tau peak, will have an influence. So if you put together all of this combination of stresses, we might expect 4 different behavioral zones in terms of liquefaction, non-liquefaction, also a safe zone. So I will use this table here to explain what are the mechanisms from now ahead. So before that, I want to clarify what is this tau peak, or also known as a tau and drain. Basically, if you perform a monitoring test, you might reach a transient peak behavior here, and this peak will be the initiation of instability in sandy soils and in terms and relatively loose soils. After this peak, might experience the so-called static liquefaction. If the soil is not medium dense, you might have a limited flow, and then when reach the phase transformation line, the soil will recover certain strengths and will follow the failure line. So I will use the concept of tau peak to explain why we can expect certain behavior in soil with the initial static shear or not. In terms of tau peak, this undrained shear strength of the soils depends on many factors. Depends on the initial static shear, depends on the density of the soil, and because of that, might be easily estimated based on laboratory tests. So there are equations available like the one I'm showing here. So the first failure mechanism I want to talk about is the one I call potential large shear deformation under cyclic loading. And I'm going to use the case of loose sand, medium dense sand, and dense sand. So in this particular case, if you look at the bottom figures, the soil experiences many cycles of loading, during which the effective stress decreases because there is a generation of excess porphyry pressure. But before the soils might experience large deformations, the soil has to develop very large excess porphyry pressure over the pressure generation, even in the case of loose soils. So in this process, for example, from this point to this point, even though the soils goes many cycles, if you look at the deformations are very, very small. And only when the liquefaction occurs at this point here, then larger deformation and flow failure might occur. This is the case of dense soil, medium dense soil. And in this case, for example, the number of cycles to reach liquefaction 38, and after that, actually the soil still can experience large deformations. In the case of dense soils, actually the soils will not experience large deformation, even though undergoes many cycle loading cycles. So in the end, in this particular case, the soil could experience large deformations, but the question is that how many cycles we need to, or an earthquake we have, and to induce this kind of failure. So potentially, yes, the soil could undergo liquefaction and develop large deformation, but the reality is only if an earthquake is strong enough. In this second case, and I'll go back quickly. In this particular case, the behavior is because the maximum shear stress we apply in the soils does not exceed what is the peak strength of the soil. In this second case, it's clear that the maximum shear stress of the soil exceeded the peak strength of the soils. In this particular case, the soils might easily reach liquefaction, and once reach liquefaction, the soil will experience large deformation. So compared to the case before, rapid or flow liquefaction occurs within a few loading cycles, and therefore large deformation might be expected, even in the range of 50% or more. In the third case, the soils does not show liquefaction. This is the non-reversal case, but at larger deformation, the soil will experience shear failure. So completely different failure mechanism. And this is because of the maximum shear stress of the soil will exceed the strength of the soil, this point here. But if you perform a similar test and now the maximum shear stress will not exceed the strength of the soils, then the soil will not develop large deformations, even though you apply 100 loading cycles. So these are the four failure mechanisms you can expect, considering the combination of the initial static shear, cyclic shear, and also looking at the strength of the soil. And this is a summary of the typical resistance of the soil in terms of alpha, the static stress ratio with number of cycles. And for 3%, 75%, and 20%. You can see that usually loose sand will, as you increase the initial static shear, the tendency of the soil to experience large deformations decreases. So it means that the initial static shear has a detrimental effect on the deformation of the soil. For medium dense sand and large deformations, it seems that at certain points there is a change in behavior where the soil starts to gain certain strength. And this was not observed for small deformations. If you look now at much larger cyclic stress ratios applied, and then we look at medium dense sand, in this particular case, the change from detrimental to beneficial occurs when we have the change between non-reversal and reversal stress. It means that when the initial static shear becomes smaller than the static shear. For dense sand, it looks like that the effect of initial static shear is not as severe as in the case of loose sand. And this is another figures maybe that can help to explain the behavior. So in here we have the cycle stress ratio evaluated at 10 cycles, 3%, 7.5%, and 20%. So we have loose sand, medium dense sand, and dense sand. Again, we have similar results, similar tendency. So as we increase in initial static shear, the cycle resistance of the soil decreases for relatively loose and medium dense sand, but quickly recovers for dense sand. And in the case of 20%, 20% was not achieved in the laboratory for dense soil. It's a very strong soils, but was achieved for loose sand and medium dense sand. And can be seen that in general, the resistance of the soil decreases until reaching the reversal line, and then there is a change, and then the soil starts to recover the strength. You can plot the same results in terms of K alpha, which is better parameters maybe, and you obtain similar results. And in this particular case, it seems that, for example, the K alpha, 7.5%, it's very similar for the three independently from the density, but the way the soil recovered the strength, it then depends on the density. In the case of dense soils, the recovery and the beneficial effect of initial static shears are visible much earlier stage than comparing with the other, the medium dense and loose soil. This is a quick comparison between the tests performed in this study with other relevant tests done found in the literature. So I'm referring here to the black line here, the 7.5%. So these are dense loose sand. The test results in here are similar trends to what was observed in simple shear tests in the case of medium dense, and also in the case of loose sand and medium dense sand. When we compare with the triaxial tests, the trend is quite different. As I mentioned before, is because the conditions or the model deformation of the same soil in triaxial parts, the simple shear conditions are quite different, and we have to be careful how we evaluate the strength of the soils, and how then we use the results. So what we notice in the laboratory that yes, we can achieve larger deformations, but at certain points the deformation are not uniform, no longer uniform in a specimen. You can see, for example, the larger deformations, the bottom part of the specimen is relatively uniform, but the top part of the specimen has much larger deformations. So we are able to identify where is this change in behavior from a uniform deformation to a non-uniform deformations, because that is a limit of deformation you can use from laboratory tests to estimate the strength of the soil. And this kind of approach has never has done properly in triaxial tests, and it's very difficult to evaluate in simple shear devices where you cannot see the specimen. But to give you an idea, for example, you can evaluate what is the difference between the vertical stress and the radial stress if you lock the deformation specimen, and you can identify this point A and point B, and this will give you a clear understanding how is the change in deformations. So you can do this exercise for many specimens, different densities and different other parameters, and you obtains a curve that summarize that helps summarize what is the limit shear strain to achieve shear band formation even in liquid fiber soils. And it is clear that the density is one of the key factors. Looser soils tend to have strain localization much larger strains, while dense soils tend to have shear bands much lower deformations. But the strain localization depends also on other factors, depends on initial static shear, depends on confining pressures. So actually, we identify other parameters, which is drain shear strength of the soils, that can capture a better way what is a leading shear strain, because incorporate the density, the confining pressure, and initial static shear. To conclude, we have used this method to evaluate what was the behavioral or back calculate or the behavior of slopes observed during or the failure of slopes observed during past earthquakes. This again is the common model earthquakes, the Takano landslide, 6% degree of inclination. This is how it looks like the slope. So the source areas in here, and what I'm showing here, the cross section here are the longest length length in here, and the soil is moved from here to here about 600 meters. We did some limit equilibrium analysis, and the factor of safety before the earthquakes was 3.1. We also did some seismic limit equilibrium analysis, and we found that the factor of safety dropped to 0.8 during the earthquakes, but it did not provide us information about liquefaction behavior. So then we did some laboratory tests. We recover samples of these poems in here. We did some laboratory tests. We compare with the Toyota sand, and we found that these poems soil behavior could be similar to a medium density sand. Then we evaluated what is the K alpha, and we use a very simple model, predictive models, where we can see that if you consider the strongest earthquake of the common mode earthquake, this model might predict liquefaction. What if you consider the foreshock, which was much less stronger, liquefaction not occur, and this matches the reality. Another case is the Niigata earthquake. We had NSPT values and observation in the field for this particular slope. There was a liquefiable soil layer quite shallow that liquefied, and then again we use this simple method, and this is the CSR line, and our observations, liquefaction zones and no liquefaction zone, match with observation from Armada in Toll 1994. So my time is finished. We'll go quickly through the conclusions. So the evaluation of the effect initial shear on the liquefaction resistance of sandy soils is significantly affected by the testing conditions, simple shear or traction shear, and we should be very careful how to investigate and use the data. The stress reversal plays a key role on the failure mode of the sand, and liquefaction can only occur under stress reverse conditions, while under non-reverse stress conditions, the liquefaction will not occur, but shear failure might occur. There are different failure mechanisms, from potential development of large deformations to flow failure to shear failure, and the most detrimental is the flow liquefaction because it happens without any warning signal. The cyclic strength of the soils, it seems that to decrease, irrespective of the density, to decrease with initial static shear, and therefore, and only under non-reversal stress conditions, then we have the beneficial effect of the initial static shear, which is in opposition of what we found at the actual tests. We noticed that when you reach large deformations in any test you conduct, the soil, even liquefiable soils, might undergo strain localizations, and therefore it's very important to understand when the strain localization occurs, because that might affect the results we have and the way we evaluate the strength of the soil. Before I conclude, I would like really thank you, the key collaborators from the University of Tokyo, Professor Junichi Koseki, my former PhD supervisor, Takashi Kyota, which allows me to use still use this large apparatus nowadays. Takashi Sado, which is developer of the apparatus, and Muhammad Umar, that was my former master and PhD student that has done most of the tests I showed today. Thank you very much for your kind attention.
Okay, thank you for the very interesting lecture. And now, actually, I think we can open for a question. I am not seeing the tab for question answers.
I think there are no questions as such, sir. I think
Okay.
Question answer session. It is.
If it comes, then only it will be there.
Yes, yes. Am I right, Professor Srival, sir?
Yeah. There is no question yet. Yeah.
Okay.